una parte di voi conosce gli episodi, cioè il professore ordinario a Dipartimento di Fisica dell'Università di Zurigo, è uno dei massimi esperti mondiali, cioè per le persone più famose nel campo della fisica teorica e della fenomenologia delle particelle elementari. I suoi contributi più importanti sono la metastabilità del vuoto nel modello standard, la formulazione della minimum flavor violation, contributi importanti. È stato visiting scientist a SLAC, fellow al CERN e, vabbè, e tante altre cose in giro per il mondo. Attualmente, diciamo, è leader di questo gruppo che si è formato intorno a lui a Zurigo e che si occupa anche di fenomenologia. Una delle ultime attività è nel campo della fisica quantistica e recentemente, oltre all'ERT avuto qualche anno fa, su queste ricerche della fisica del flavor, dal 2021 lui è membro di questo Science Policy Committee del CERN. Magari ci dirà lui qualcosa in questo, perché ha a che fare con le scelte politiche, scientifiche politiche della fisica della fisica dei corsi. Lo ringrazio personalmente e a nome del comitato organizzatore e sono sicuro che farà come vedrete delle lezioni alla lavagna veramente godibilissime, in particolare per i Grazie.
Grazie, veramente un piacere essere qui. Non avete detto che venivo all'Università di Napoli prima ancora di essere laureato, credo, quando lavoravo con Giancarlo un po' di anni fa, diciamo, tanti, e quindi sono anche...
Okay. It's okay? Okay, so I now switch to English and try to be professional. Okay, so yeah, what I will try to discuss in this lecture is a bit a discussion about the standard model and why we want to go beyond and how to go beyond considering the standard model as an effective theory. Please tell me if I don't know, is it okay, the audio? Okay. So maybe let me give you a tentative plan of the lecture, okay? Because we have 3 lectures. So this first lecture will be really an introduction, where I hope to tell you something that probably most of the people in the audience know, but I think it's always good to remind me. So we want to discuss why we want to go beyond the standard model. We have to look first to the standard model itself, okay? So really here what I want to discuss is what is the standard model, with some historical remarks, which I think are important. Then I will give you some basics of effective field theory, which is really this general context on which we think we see the standard model as part of effective field theory. And then, I mean, the reason why we want to go beyond and we really give a closer look to the Lagrangian of the standard model as viewed as an EFT Lagrangian. Sorry, write a bit small, so if it is too small, please tell me, okay? And then the second third lecture will be a bit more technical, so this will be hopefully very general. Here we'll discuss a lot about accidental symmetries, which are a very important tool, which somehow is not discussed too much. This is what I want to stress. Then we'll discuss about neutrino masses, proton decay, and also how this fits in this picture about the standard model, about flavor symmetries. And finally here, we will discuss what now is called the SMEFT. So really to the Lagrangian of the standard model with all possible extra interaction and really, after discussing accidental symmetry, will be important. Will be a key element to discuss what is this math Lagrangian here. So maybe for those of you who know the story, so this is a Lagrangian with a lot of parameters, and I think it's a bit getting lost in this parameter space. This is why it's very important to discuss this issue of the symmetries. Symmetries are really our guiding tool in this big parameter space, which then, once you understand the symmetries, it's not too complicated. There are not too many arbitrariness, but really symmetries provide the guide. But again, before discussing these things, let's go to the first step here. Okay, so this was just an intro. It's really high, this blackboard. So what is the standard model, okay? And I think there are some basic principles which we base our theories. First of all, it's a quantum field theory. Vector is a renormalizable then I will only speak about GFT. This is really this is the class, okay? So in terms of theories, it's a renormalizable quantum field theory, which is very important. Then, within the class of quantum field theory, the standard model has a very important property that the long-range forces, so the standard model is the theory of the three long-range forces that we know in nature since a long time, which are electromagnetism, weak interaction, and strong interaction, which historically have not been always called long-range, but nowadays we really think they are all long-range forces. So these long-range forces, we think they are described by the principle of gauge invariance. So gauge invariance is a principle, okay? So we think that when we put, so this is a quantum field theory, and we'll discuss a bit more in detail what quantum field theory means, but when we have a field, for instance, let's say a fermion field, and we have several of them, so I put here in index alpha, this field depends on the space-time coordinate, sorry. The principle states that we can basically change the phase of this field anywhere in space-time. So this is a fermion field. So this is a generic phase transformation. So this lives in some group space denoted by alpha. And the principle states that, okay, my Lagrangian should be invariant under a change of phase of this field in this group space. This is the principle of gauge invariance. Because of that, because of this principle, you deduce completely the interaction under the forces. And the specific realization is that, okay, the gauge invariance that we have in the standard model is this one. What this is. This is the specific. So the general principle of gauge invariance and the specific gauge symmetry is this one, as you know, which indeed is the symmetry of the strong interaction and then weak and electromagnetic interaction. So this is really what we understood after basically 100 years of history. I will then tell you a bit more about the history. But really these three forces are associated to a very important principle, which is gauge invariance, and a very simple gauge group. Finally, okay, here it's difficult. I wanted to continue the list of the basic principles, but then we have to discuss which are the matter fields. Which are, so the matter field in the standard model, so if you want, this is the statement about the forces. The matter field are three families of quarks and leptons, which, okay, yeah, I can write them here. So what I write here is psi, okay, actually in the standard model specifically is this set of 5 different fermionic fields. Each of them, right now, I will discuss in more detail the assignment, but each of them have different quantum numbers, means different representation under these case symmetries, okay? And also have this extra index, which is what we call flavor. So they appear, so this I goes from 1 to 3. So basically we have 3 times 5, 15 independent fermions, which means many more degrees of freedom because each of them has the quantum number related to the English group. So the degrees of freedom are much more, but the basic elements are 15 independent objects. And finally, at this level, okay, we will see more tomorrow, there are a lot of extra symmetries which appear in the standard model, especially because of this redundancy in the flavor, but also because of other reasons. So there is a lot of extra symmetries which appear in the standard model Lagrangian, which we don't know why it is there, which is not related to this. This is the local symmetry, okay? So actually, at this level, there is a lot of global symmetries, like baryon number, lepton number, all these things are related to this assignment of which are the matter fields. And finally, then there is a symmetry Bergen sector, which is, as you know, due to a single field, we introduce a single scalar field, the Higgs field, which has a well-defined transformation property under that group, which is a singlet of SU3 color, is a doublet of SU2 left, and there's hypercharge 1/2. So we introduce this object. This object will build the potential such that the expectation value of this field is different from 0, and this, because of that, we have the spontaneous symmetry breaking of both the local symmetries, particularly what we break is SU2 left cross U1 that goes into the electromagnetic subgroup, and also we break explicitly some of the global symmetries. So actually, there is a spontaneous symmetry breaking of both, local and global, but plus there is an explicit breaking of the global. Okay, we'll discuss all these things in more detail later on. I just want to give you, if you want, the definition. So if I go to a different planet, I have to explain what is the standard model. These are the set of rules, which are simple, pretty simple. So it's a quantum field theory. This is the big container. Gauge invariance tells you how the force acts, and then we have to discuss which are the matter fields. Okay. I don't know. I mean, I don't know the audience, so how maybe this is totally trivial for many of you, but I think it's important to.
Nothing is trivial.
Okay, thank you.
We can assume.
But do you really think I need this microphone? I hate a bit the return, but. Okay, it's because of the video. Now, before starting to discuss all these things in slightly more detail, you see, it looks like a rather simple description. And I think, sorry, I think about this when I explain to there are probably a lot of young people who now find this in the textbook, you open it, this is the definition, you take it, fine. The model took a long history to arrive to this point, and it was non-trivial. Okay? And this is important to stress it now, especially to the young people, because now we want to go beyond, will not be an easy story again, and we have to be patient. Okay? Like, I mean, humanity has been patient for 100 years basically to build this stuff here. So let me give you this very little, very a bit biased historical remark how we arrived here. And again, please interrupt me anytime. Okay, so this is maybe you don't want to interrupt me now, but later on, if there is something not clear or too small, tell me. So I want to do this historical remark. Since the standard model is really the theory of these three forces, I think it's interesting to think, I mean, how we arrived there, and it's really an interesting story that starts parallel with the three forces. So I was chatting with ChatGPT how to explain the history of the standard model, and with some back, I mean, at the beginning he gave me a terrible answer, but then afterwards we came up with this idea, which is the following. It's really the story of the three interaction, okay? Which, so I would summarize it like this. So there is a story of electromagnetism, of the weak, and of the strong. And together with strong we put flavor, because it's important. And then we have force together. So this is a bit the theory side, and then we have the experiment. I was hoping to do this on a long lecture because it's long, but let's see how it goes. So everything starts somehow here. Maybe if you want to take a start, is the actually I have it here. I don't want to give you wrong dates. 1928, there is a Dirac. Okay, Dirac equation, and then this discovery of the positron in 32. Soon after. And then it took, now I go fast. Then in basically 1947, 49, we basically arrived to QED. So with the famous work by Schlinger, Tonaga, Feynman, Time, that finally really understood how to incorporate electromagnetism with the principle of quantum mechanics, gauge invariance in a full-fledged quantum field theory. So what I want to say, because this is really the first quantum field theory we have seen in nature. We've seen at work. And we really see at work because here there was a crucial test. Okay, there was the lamp shift, and there was the G-2. So this is really somehow that time that basically gives the confirmation that this is the theory where you can compute things and it works. So this is, I would say, it's really the foundation phase, which you see, it's basically 20 years, foundation of QFT as a tool to merge quantum mechanics and special relativity.
So, just for historical reason, this is important according to me. Lamp shift G-2 data was before theory. So
yes, absolutely, yes.
So post 1% measurement said you have to do better than 3-level calculus.
Exactly. And then you have the theory that was able to show that what you get is correct, absolutely. So okay, here not super, and should not forget here, of course, there is a key ingredient, 1934, which is Fermi. Okay. Fermi theory with interaction happened there. However, at that time was kind of stayed there. Okay. And then after 50, so more or less at that time, after QED was understood to be, so at the end this is a kind of closed story, Then it started all the interesting, intricate development of the other interaction, which I probably have to go to the other part of the blackboard, but clearly a very important work is Young Mills. Young Mills is an attempt to do something beyond the abelian gauge theory. Basically, with no application at that time. There was just an idea there, but that turned out to be important. And then, basically, the evolution of the Fermi theory was thanks to here that there is the story of the hypothesis of parity violation, the discovery of parity violation. So we put it here, Wu experiment, which I think is 57. And then there was the V minus A theory. The V minus A theory is really the evolution of the Fermi theory in a form which is really the one now defined in the textbook with the V minus A interaction, which was a bit different than what the Fermi had. And this was by Feynman and others. Okay, and then there were really, soon after, you see, this is where the things start to cross. Here in 1961, there was the wars of Glacier, and it is really the first hypothesis of merging the algebra, okay, of these two theories, because given the success of QED, you want to make a gauge theory also for this, and then you understand that you start to put them together. And then, okay, then the story is long. I don't want to bore you too much with the historical remark, but again, it was a highly non-trivial story. Here in 1963, there is the work of Cabibbo, which on the other hand, Cabibbo is very important to somehow understand how the weak interaction also connect with the strong interaction with flavor. And then there is, okay, here I put it here. Then there is the Higgs mechanism in 1964. And finally, maybe I put it here. I hope it's not too small, but probably for the video it's too small, but okay. So clearly here, a very important work is the Weinberg-Salam theory, okay, which is a theory of leptons only. And finally, in 1970, there is the Jim mechanism, which states how to put also the quark into the game. And here I forgot about the experiment. In the meantime, also, it looks like the strong line is a bit silent, which is not, because then there is the hateful wave in 1961. So the quark hypothesis, which is in 1964, so here there is quarks, the quark model. And then there is, I think in the, what is it? Here there is the deep inelastic scattering, which was a crucial ingredient to test the strong interaction. And finally, also why I want to discuss all this in this context, that in 1972, okay, there is the normalization of spontaneous symmetry breaking, the work of Toft and Weltzman, that demonstrate that the spontaneously broken theories can be normalized.
There are two
missing things. I know there are a lot of missing things, but
no, but one CP violation.
CP violation, yes, in 64. I will come back to this variation later.
And also another thing, because they get really offended, I know. The Japanese.
Nambo, yes. Okay, this is a partial list. I just want to show, just to give you the impression that this is a complicated story. And so this was 69. Sorry, let me converge. Okay, then there is in 1960, 73, here there is the neutral current. In my opinion, I mean, a posteriori, really the observation neutral current at CERN was really the first clear demonstration, okay? Actually, they should have got the Nobel Prize. Why they didn't got it, it's really, I think it's a mystery. But it's a mystery, is the fact that...
Gargamel, you mean?
Yes, it's the fact that then in 74 there was discovery of charm, and then everything, okay. Then there is the famous November revolution with the gypside, and they discovered. Then afterward there is a very nice experimental story, but the foundation of the standard model somehow ends here. Which again, if you go from 1954, so it's got 20 years, and probably a bit more of an integrated interval. Also here is, I should put asymptotic freedom, okay? Which also happened in 73. So finally here, all the pieces get together to end up with the SU3 cross U2 cross U1. And then it was a very successful experimental story on also, I think at this point, 74, also look in the history, the word standard model, standard theory start to emerge. Actually, at the time was a theory with only two fermions, two generations, sorry, which then soon after, in 77, there is the piece of becomes a three generation. And actually, it's a pity that the two generation standard model lived a very short time. Why is it a pity? Because it's the two generation standard model is a renormalizable quantum field theory, exactly like the one we have now. So having it a bit longer lifetime of this theory would have been more beneficial for us to understand that if you find a renormalizable theory, doesn't mean that it's the end of the story. And in the same, we've seen it already with QED. QED is a perfectly renormalizable QFT. And it was considered a done deal. And then you understand actually this is part of a more complicated mechanism. Then you have the standard model 2, then you have to go to the standard model 3, and then what else? The point that when you end up on a renormalizable quantum field theory, this is what we'll discuss more today, it's difficult to go beyond if you don't have an experimental clue. Okay. And the other things why I wanted to emphasize all this is that the work of renormalization of spontaneous breaking was essential at that time to really start to believe the standard model works, because then you go to calculation, process calculation, compare with the data. Now, again, what I will try to convince you in this lecture that actually this is a problem. It's not it's a problem, it's a fact, but it's a bit of a fregatura for us, in the sense that that means that you have a theory which is screened from what happens in the UV. This is the message, okay? So when you end up in this case, from QED here, you have no clue that you have to go beyond, but firstly, okay, there was something else happening that you couldn't explain. Again, also here, now we know that there is something that we cannot explain, like neutrino masses or dark matter. Especially neutrino masses is a very clear indication that our theory is only an effective theory. But the indication to the scale is much more vague. Okay. Okay, so this was just to tell you that the story was complicated. Anyway, so we have to be patient. And so this is for the young generation. It took 20 years to basically arrive to the first QFT, and then other 25 years to arrive to SU3 cross SU2 cross U1. And then it took other 35 years to test it after the discovery of the Higgs boson. So things takes time. Okay, so having said all that, let me now start to be a bit more. This was really a warm-up. Let me give you some discussion of what we mean by effective field theory. sorted. You know, nowadays everybody speaks about EFT, but actually the correct name would be effective quantum field theory. So okay, we're discussing quantum field theory, but effective. Effective means you will see that have an intrinsic validity regime. So we need. So again, probably most of you are familiar with quantum field theories. For those who are not, I think
Si era scaricato. Allora, magari lo togli e poi.
Finalmente.
Vedi,
Scusa, vedi se si sente.
No, but in the room, clearly here, the point is the
No, he said it's okay.
Okay, then it's okay. I can try to shout more, right? If you don't. Okay.
He's a good singer, eh?
Yeah, well, I was, now. Okay. So, again, I want to give you a very brief glimpse of what is a quantum field theory, or which are the ingredients for those who are not too familiar. So, what is a quantum field theory? In a quantum field theory, our basic mathematical tool to describe what we see are fields. So, there are no particles, there are no waves, there are fields. So, and then what we discuss, however, is with the principle of quantum mechanics, we discuss probability amplitude from a field configuration to a different field configuration. So my initial state will be described by a certain field configuration at an initial time, and we want to understand which is the probability to go to a different field configuration at a later time. Okay, so this is I want to evaluate this probability amplitude. In quantum mechanics, everything is described by probability amplitude. Then, of course, probability is the modulus square of the probability. So this is this field configuration, okay, for our experimental friends. It is described, okay, for instance, some initial particle with certain momenta, so the free field, so the field by the field that somehow at large distance is described by initial state, and finally have my final state. Okay. Here again, I try to be not too formal to keep everybody important. And there is a recipe how to evaluate this amplitude. Again, we are in quantum mechanics, so all paths are allowed. So you have to evaluate all paths, and you evaluate the probability amplitude is given by an integral on all the paths for your field configuration on this given by this boundary condition. And then there is a fantastic object, which is our action, S, which is a function of the field, which tells us the probability. Okay, it's a complex quantity, and this, we write it as an integral of an object, which is the Lagrangian, which depends on the field and the derivative. You see, this is the, so you evaluate all possible trajectory that give from the initial to the final configuration. They will be associated to different action. And then you see this is the path integral formulation a la Feynman. You see that when h bar is the fundamental Planck constant, you see that the limit where h bar goes to 0, this is a super oscillatory term, and you are dominated by the case where this is a stationary point, which means the classical trajectory. So the classical trajectory, you know, from classical mechanics, the principle of minimization of the action comes from here. Well, you can recover classical mechanics in the limit when h bar goes to 0. If h bar is not 0, then you have the fluctuation, the quantum fluctuation, which are controlled by how far you are from the classical action. Okay. So everything, our theories are described by give me an action and I tell you the probability. Okay. So this is the ingredient. Now I want to discuss a little bit possible action, or better, the possible Lagrangian, which are, so the action we write it in a bit of our principle, we write in terms of local Lagrangian, so Lagrangian where the field interact at the same space-time point. This is because of locality, causality, otherwise we would have problem with causality. So I think it's very interesting to understand the dimension, the dimension of the field, because this allows to make a lot of consideration about the relevance, yes, of the different fields in the. So now, from now on, I will work in the beautiful natural units where h bar and c equal to 1. So this, you see, now you will not see it anymore. But it's there. As you all know, in this, when you go to these natural units, everything can be measured in terms of energy. So we can, the different dimension of the only physical dimension is energy. So we know that, for instance, okay, energy and momentum with this square bracket is how much they scale with energy. They will be for me +1, which means they scale as their energy. Okay, energy momentum at the positive dimension of energy, while distance, okay, or time, and of course time incorporates will have negative dimension, okay, because we know that x dot p is equal to h bar, that is 1, so they have to be inverse. Okay, so these are the dimension of the usual quantities. Now we want to define the dimension of the field. Okay, probably this is known to all the theoreticians. How we get the dimension of the field? Well, we get it from the fact that the action is as a dimension of an action, but when we take h bar to 1, the action becomes a number. H bar is the quantum of the action. Okay? Classical mechanics is the limit where the action of a certain transition is much bigger than quantum of the action, which is h bar. So my action is a pure number, which means that my Lagrangian density, which is there, since it has to be integrated over d4, this will have dimension +4, dimension of 4 power of energy, because it goes here with the -4 from the d4x to make something which is dimension 0. And this is what we use to determine the dimension of the field. We determine the dimension of the field from the kinetic term. So the kinetic term in the Lagrangian for a given field is what allows us to determine their canonical dimension. So if I, for instance, if I have a scalar field where the canonical, well, the kinetic term is this one, probably, no, this is a scalar field. What defines a scalar field is this quadratic term in the Lagrangian with two derivatives. Since I have two derivatives, the derivative brings is 1 over x, 1, so it goes like energy squared, or brings two momenta. So this term has to be dimension 4 because it appears in the Lagrangian. So the dimension of phi has to be +1 because I have 1 from this 1, 2, 3, 4, to end up with 4. Okay. If I put what about the fermion field? The fermion field here is defined by the Dirac Lagrangian. So here there is a single derivative in the Lagrangian. So psi, there is only one energy here, so these two should make 3, so this has dimension 3. And then we put the gauge field. These are the ingredients that we have in the Star model. These also we have dimension 1. This you see from the Maxwell action. Again, from the basic part of how the field appear in the Lagrangian, I deduce the canonical dimension. And finally, last step is now I want to define the canonical dimension of the coupling. Okay, when I put now interaction term. Coupling or one of operator. So, for instance, if I put a mass term in my Lagrangian, okay, this has to be dimension 4, okay? Which, because it appears like this in the Lagrangian, which from this I deduce the dimension of m, okay, that probably you know, as a dimension of energy, okay? Not surprisingly, and also in the case of the fermion, this is the mass term. Here I have, this is not surprisingly in the Lagrangian, the master appear with 1 power, the here it appears with 2 powers. So again, this is both and a dimension of plus. Then we have the standard interaction that we have in the standard model, like gauge interaction, G, A mu, psi bar, psi. So G, alpha is a number. So this has dimension 0 because this is already dimension 4. Okay? The Higgs self-interaction also is a number, and also the Yukawa interaction. Because this is dimension 3, 4, so 5. So this type of different scaling is very important in field theory to understand how a certain interaction plays a role, how it plays a role at high energy or low energy. So this interaction, we call them relevant. This we call them marginal. And you can easily understand that there is always, once you describe how many fields you have, there is a very limited number of relevant and marginal interaction, while there is an infinite number of irrelevant interaction, which are the interaction where the coupling has dimension of inverse of energy. Yeah. Let me put one example here. For instance, the Fermi theory, we have so here G, this here, sorry for writing, but here you have 4 fermion field. 4 times 3/2 makes 6. So G has the dimension of -2. Is the dimension of inverse of energy. Yes. Yukawa is marginal. Sorry.
0.
Sorry. Thanks. I do horrible mistakes often. Thanks for sharing. On the other hand, the Fermi coupling is irrelevant. Now, this is a bit of a name. Actually, of course, it's very relevant, the Fermi coupling, but it's irrelevant is that it gives rise to an interaction which becomes very weak, not surprising, the weak interaction at low energies. And high energy, the interaction grows with energy. Okay? And the key point is that if there is a finite number of relevant and marginal, and a huge number of, clearly, if I put here 5 to the 6, 5 to the 8, so clearly the possible list of operators which give rise to relevant the relevant operator is infinite, while this one is finite. And as you probably know from your PhD course, this is the set of operators that give rise to what you call the classical renormality. That is, how many minutes do you have?
3 minutes.
3 minutes. So then we will discuss more after the break. But so if you have a theory that contains interaction only up to this point, when you look at higher order interactions or higher order iteration of these terms in your Lagrangian, you have to integrate over all the fields. So this, you have to take into account all the interaction to higher order. This is the so-called loop expansion, which I'm sure you know. What happens is that you encounter apparent divergences, which leads to a renormalization of this coupling. But that's it. So you have to adjust this coupling to absorb these divergences, which really I have difficulty to say divergence because there is nothing divergent. Okay, it's just it's a mathematical artifact. It's a mathematical artifact related to the fact that we want to extrapolate the behavior of the theory up to arbitrarily high energies. Doing so, we introduce artificial divergences, but these divergences can be reabsorbed into the redefinition of the coupling. Okay? This is more complicated here. Requires a bit more technique. This is why, for a long time, these non-renormalizable theory or effective theories generically have been looked with skepticism. And here, I forgot when I was doing my list of works. After 74, when people understood, okay, people were so happy, okay, now we have a renormalizable quantum field theory, we have the standard model, but then in the meantime, there was basically the history of the 3 weak, strong, and the Majorana somehow stop there. But in the meantime, there was a lot of independent parallel theoretical works. In particular, very important work was the work of Wilson on the normalization, okay, of what it means to normalize a theory. A normalized theory is just a way to reabsorb heavy degrees of freedom into a redefinition of. And from that point of view, you understand that there is really no, this separation is just a technical separation which makes life easier if you stop here. But these terms are perfectly allowed. We don't spoil anything about your predictivity, provided you state up to which energy you want to describe, which is your energy range of process that you want to describe. The ambition to describe everything up to infinite energy somehow makes no sense. Okay. But these theories, if you stop here, in principle, could be valid up to arbitrary. They don't tell you where their validity stops. Again, if you look at QED, you have no clue where QED breaks down. We know that breaks down at the retrowave scale because then it's embedded in S2 plus U1. It's a different theory. Okay? But you don't have an indication if you just look at alpha QED. Not, you have to see extra term like the Fermi theory. Okay, so maybe this is a good point to stop, and then we continue the technical part.
Now we have the coffee break. We will see here at 15 to 12, and see you. we have a 30-minute session, question and answer. Please.
Okay, so let me continue basically where I interrupted. So I want now to convince you why this interaction, which actually is somehow the Fermi theory type interaction, which is interaction with four fermion, that has a coupling, like the Fermi coupling that has energy dimension minus 2, so that we can write this coupling as it's natural to write it like a coupling divided by a mass squared, because that's dimension of 1 over energy. But I want to convince you that we can do calculation with this theory property, and also to show why apparently is a problem, why in practice is not a problem. And this is true for any non-renormalizable interaction. So, for instance, with this interaction we can compute a scattering between four fermion. Okay. Here again, sketch it. I will not do a full calculation, but I will keep track of all the important kinematical dependence. So here, for instance, we have a scattering of 2 fermion going to 2 fermion, so clearly this can destroy 2 fermion and create 2 fermion in the final state. If we compute this amplitude using this interaction at 3 levels, okay, this is the Lagrangian density, you put it in your action. At the end, probability are always numbers, okay, so you have to have a result which is a number for this probability, and this number has to be proportional to the coupling, okay, because if there is no coupling, there is no scattering. So without any calculation, you understand that there will be some prefactor, but has to go like G, which has dimension of energy squared, times, and here there will be some momenta. 1, 2, and so on. And they're not generically the momenta with energy. Okay, so clearly this amplitude has to grow with the energy. Because of the kinematics and because of the energy dimension. So clearly if I have a coupling which has 1 over energy, to get something with probability amplitude will have to be compensated by the energy. So and as you know, if you do the full calculation, you get exactly something like this. And this is why we call this a kind of irrelevant interaction. When the energy is small, the interaction goes to 0. Well, actually it doesn't go really to 0, because at some point then you will have the masses here of the particles. So the muon decays, okay, even at 0 energy, but because this is the energy in the final state of the decaying particle. But indeed, this was a well-known problem that this amplitude, on the other hand, clearly if you go to arbitrarily high energy, this cannot be, so then the amplitude probability becomes bigger than 1. So you already have an indication that this theory works well at low energy and has problem at high energy. So what happens with the renormalization? Okay, so let's try to compute a bit naively what happens when we look at the one loop. Okay? Don't want to do the full calculation, but we can understand the behavior of this amplitude just by naive dimensional consideration. So here, this amplitude has to go like, so I put 2 times the interaction, okay? So here, there is my coupling G appearing twice, so this will go like G squared. Then I have a loop integral. I call L the loop momentum here. The rule when you do calculation, you have to put the 16 pi square here. And then we have propagators. Okay. But here, okay, let me be a bit naive. I have fermion propagator, 2 fermion propagator. And then there will be a numerator which will depend on the momenta of the particle. Here you have to do all the Dirac algebra, but it doesn't matter. The key point I want to illustrate here is that you know how these amplitudes scale with this variable L, which is the loop integral. So this scale like there is a d for L, by the phase space or integration of the loop variable, and then there is a 1 over L squared because of the 2 propagators. The fermionic propagator brings 1 power of energy. So you see that this integral is badly divergent for L. So this integral makes sense only if you put here a cutoff. that we call it lambda UV. So this integral cannot be valid at arbitrarily. So L denotes the energy of this virtual particle. You see, again, I already knew it here that this interaction cannot be valid up to arbitrarily high energy. It was already an indication there at 3 level. Now I'm trying to put it in the loop. If I integrate to arbitrarily high energy, clearly make a mistake. And this mistake I say it from the this divergence here. Still, I can understand how this object depends on this cutoff. Okay? And again, this I derive it by dimensional argument. Okay? Okay, all these things has to be, it's an amplitude, so it has to be a number. Okay? So I have my G squared. These things I want to see the leading divergence is just given by how this diverges with L. You see, this is the, I have L to the 4th power divided by L squared. So this will grow at most with lambda UV squared. Then there is a 16 pi squared because of the loop integral. And then there will be some other kinematical factor which I generically denote by E squared. And I know that this is E squared because overall this has to be a number. So this is energy to the minus 4, energy squared, so again, a number. Now, you see clearly, if I put lambda UV to infinity, this is a problem. I cannot, it's a bad divergence. However, again, already from the 3 level, I knew that this theory could be valid only up to, cannot be valid up to arbitrary energy. So actually, let me rewrote this as 1 over lambda UV, and I define to be lambda UV the what it will be E squared divided by lambda squared. So clearly, this lambda UV, which is there is an indication of a scale intrinsic in the coupling, tell you when you put all the other factors at somehow order 1 factors, clearly this theory makes sense. E for E, then you can decide how close you want to go, but certainly E has to be smaller than lambda. And then if I put here, this lambda UV, if you want, is an indication that we already have from the strength of interaction that the theory has a. So here, if I do my integral, okay, and I put the same cutoff lambda UV, which is the one indicated by the coupling, what I get here, now I do my substitution, here I get 1 over G squared will be 1 over lambda to the lambda UV to the 4th, then I have this lambda UV square, and then I have the 16 pi square and E square. So you see that this will go away, and thus this becomes 1 over 16 pi square G E square, which is a small correction with respect to what I had at the 3 level. Okay, all this is a bit naive. I don't put the order 1 number, but the physics is correct. That is, at the end, if you restrict your validity of the theory up to energy or momenta which are well below this cutoff, there is no problem. And then the loop correction will give you small correction. Okay. What is the other problem that what people were not so happy about this normalized interaction is that, okay, here these things somehow correct this interaction with something which is small if the energy is small. Another problem that arises, and now you can consider other type of interaction, for instance, something like this. Now I put it 3 times the interaction vertex, and then if you compute this, you will get your G2, okay? And again, if you do the calculation, you see that in this case you will not have a divergence, okay? You have only a logarithmic divergence, but clearly there is still a divergence, so you'll get something like this. This is e to the 4th power, correct? So this is actually like this, and then there is some of this means that you generate new type of effective interaction, so that's something with our experience that you have to put in, but this will have a much higher suppression with the energy. So it's a much more suppressive effect, which means that our tower of effective operator is an infinite tower. But your precision, which you want to determine things, will depend on which is your energy. Okay, this is if I rewrite it in terms of these things here, will be like E over lambda uv to the sixth power, but here we have only the second power. So clearly, if you are at low energies, okay, your effective theory contains only, you have to take only a finite number of operators, which is well defined. You can absorb all these divergences, no problem, and the number of terms that you have to include is fine. Okay. This is now completely widely accepted. There is really no conceptual difference between the normalizable theories and the non-normalizable one. So the only difference is that when you have to deal with interaction like QED, you have only one coupling alpha. This coupling alpha, it depends also logarithmically on your freedom. You redefine this coupling and you are insensitive to this. So the message I want to give is that in principle, if you knew which is your UV completion, actually measuring, suppose that somebody tell you actually the true theory as alpha at some scale, alpha is equal to 1 over pi. Suppose, and then you measure alpha at low energies, you will see a different value. Actually, this the running of alpha from UV to low energy contains all the information, all the history of the degrees of freedom that are between where you measure and where your UV theory. The point that nobody knows which is the UV, we only proceed bottom up. Okay, so we measure the value of alpha, and the fact that this value can be normalized simply means that we have no way to understand which is the UV. On the other hand, if we see an interaction of this type, we are more lucky because we see that this interaction at some point breaks down. So we have an indication of an intrinsic breakdown. The theory, if you want, the theory has to break down before this case, can break down much earlier, okay? But at some point it will break down. Okay, so this is why, if you want, non-normalizable theories are easier if you want to extend them, because they already have an indication, an intrinsic indication of where you have to go. Now, where we are now with the, so that was the general discussion. So where we are with the standard model.
Sorry, a question, just a story really, but because now it's interesting. When they did the Gargamel, they knew that was lambda was MW.
Yes, because this was after everybody.
So they knew where to look for.
Yeah, and again, this is already intrinsic in the Fermi theory. But then, for those, so in the Fermi theory, there is only one scale, which is when you look at the Fermi theory, G is one of V squared, where V is the back expectation value of the Higgs. Okay? And now this is also equal to G squared divided by 8 and W squared. Okay? So the break between G and NW is something that if you only look at the effective theory, you don't know. Okay? That is the limitation of the effective theory. They tell you that V, what is V? Is 246 V. Okay? Maybe this is a square root of 2 or whatever. Or less is like this. You see now, we know now, okay, that actually this is, if you want, V was like NW divided by G. Of course, there is no way to distinguish between G and NW looking only at the Fermi theory. It's only when you find that model, then you really embed it with QED, then there was a way to distinguish the So, indeed, the effective theory, but this is an important point, and we will come back also more many times. When you see an interaction of this type, you know the upper cutoff of the theory. Breakdown can happen at a much lower scale. So, for example, here the cutoff was 260 G. In practice, the breakdown is at 80 GV when the W here, because the coupling is small. But if the coupling was bigger, if the coupling was 4-5, it's possible, then it would really go much higher. Okay? So that is an important point. For instance, I anticipate this, we'll discuss it more tomorrow. I mean, the only clear indication we have nowadays of an interaction of this type, so a neuronormal is from neutrino masses. But there, the effective scale is huge. So really, you don't know where the next step is. Could be very high, could be much lower. But there are other indications which are telling us maybe it's low. Okay, so let me summarize. So the model point of view on the standard model is energy that we have this theory of the highest particle energy at the top, then we have the Higgs, then we have the W, then we produce here the deep work and all the other stuff. So this is the standard model spectrum. And clearly here there is a mass gap. This mass gap is all the experiment done at large hadron collider. We've not seen anything just above the top. And you know that there is a, so these are all physical state. There is a what we call the D, which is the lab expectation value of the Higgs, which is 140. All these masses are proportional to this quantity here. Probably not. Sorry. Too small. The idea is that this is just the randomizable part of an effective theory. I think but there is a standard model. This standard model are all the operators with dimension up to 4. Compatible with this H symmetry. And the mass and the fermions which I told you before, and now we will look at. The idea that in principle there can be, actually we expect generally to have other terms that I write now generically like this. And here, and this is, I have to start with operator dimension more than 4, that is dimension 5. Okay. All this contains, this is a horrible notation, but this is what you find in the book, so they have to introduce a scale. Okay. In principle, there can be many scales. We don't know how many. Probably, maybe even infinite, but since we don't know, we just put one lambda, and somehow, because also we don't know the cap. But clearly, there has to be a scale suppression, and this scale has to be somehow above these 250 GeV because we have not found anything else there. And this we write in terms of, unless you are able to excite a new degrees of freedom, the general description of total energy is something like this. So there is the low energy part, or if you want more technical, this is really the long range structure. No matter how complicated is the UV, if the UV contains, and this is what the experiment tells us, the long range forces are controlled by this symmetry, and the only fermions, okay, which we observe are the least I gave you before, all the rest will give rise to contact. That is contact interaction among the standard model field. What is nothing but, at the end, the multiple expansion in electrodynamics, for those who know that, is exactly like that. So the more you look at large distance, the only thing you observe here are the symmetries emerging and the property emerging at large distance, which are encoded here. All the rest are higher multiples, which are suppressed by escapes, and only when you look closer you start to see. And now, just to close this general discussion, for instance, here, now there's been a lot of discussion about we can do effective theories here of the low energy part of the standard model, like current perturbation theory. So here, for instance, we have a theory, if we are at energy well below the doublet this here we have a theory which is just based on electromagnetism, so QED times QCD, so well-defined theory plus performance. And nowadays, I mean, we understood how to describe what happens here at the scale of the B physics or even a bit higher. That's enough. Actually, this is what you need, and you can do arbitrarily high precision, okay? Because you have to list all the terms generated by integrating out, by describing the effect of the W, so just by a generalization of the Fermi theory with few couplings, not many. The idea is that the same could happen here for the standard model. Okay, so what I want to discuss, so again, why is difficult to go above? Because we have very few indication about this term, and because the standard model is normalized. So when I measure the coupling, I don't have a clear indication of where is the breakdown of the theory. What's more, this is a very important concept. In the value of the coupling of our theory, there is sensitivity to the UV. However, this sensitivity is just reabsorbed in the definition of the coupling. Since I don't know which is the UV, I cannot extract. How to go beyond? Of course, the best would be to do an experiment and see some new contact interaction. That would be easy. Okay? And that, of course, is one way. And then we have to classify and list this interaction and see which is the best way to see. On the other hand, from the theoretical point of view, however, it's also interesting to understand if there is something that we can extract from the standard model part, okay, which are the most naturally UV theories, or which is the structure of this operator such that all this makes sense. And the standard model Lagrangian is sufficiently peculiar in terms of symmetry and structure, which I think contains an important indication. This is all what I want to discuss in the rest of this. So let's finally look at the standard model Lagrangian. So the standard model Lagrangian, which again is something that I write according to this rule, is as a following structure. Sorry, I need to do a better notation. So there is the pure gauge part, okay, that contains only the gauge. Okay. Then I have a created term of the fermions that contains the fermions and the gauge field that we call the gauge field generically. Okay. Then I have the Higgs potential and kinetic term that depend on the Higgs and the gauge field. And finally I have where I have the Higgs and the fermions. So these are the four sectors of the standard model Lagrangian. Okay. Now, the gauge part is nothing but a generalized Yang-Mills Lagrangian, okay, which is just write it as I guess you know what is the gauge Lagrangian, right? Then you have other terms in the so this one sorry for it. Okay, the only thing I want to stress here is that this depends only on three couplings, which are the three gauge couplings. Okay. So here there are three arbitrary parameters, which are the gauge coupling, which, if you look at their value, coupling run, the value at the electroweak scale are very natural, in the sense that they are all order 1. So the 1 is 1/3, 2/3, 1. Amazingly enough, really like this. Alpha electromagnetic is 1/. But if you look at the coupling of the three gauge fields at the electroweak scale, are 1, 2/3, 1/3, roughly speaking. Okay, not very different. So very simple, and they run with energies, but this is a very simple. So only three coupling. This part here, so here we have coupling. Here there are no couplings. But let's look at that part of the Lagrangian. That part of the Lagrangian is completely dictated by the quantum number of the fermions. Okay. It's just a generalized Fermi theory. This index psi, which is the indices of the generation, and we have a sum of psi, which are these 5 different fields, which I call them Q, U, V, L, E, and then it's just psi bar I is less. Where this slash is the covariant derivative, U is, and here we have the covariant derivative for the three fields. And here, of course, you have to put the different generator for the different field, but physically it's the same story, okay? And these things are related to how the fermions transform under our group. And so let me try to probably I can read this because probably you know. I give you the table of the fermion. Okay. So we have to then to describe this part. We have to say how the fermion transform under U3 cross U2 cross U1. We have the fourth tablet. So forks are triplet under SU3. So this is tablet under 2 left, and there's a specific other chart. Q right is also a triplet of color. It's a singlet, and it's a singlet here, and this is a triplet. And then we have the leptons, the lepton doublet, which now leptons are singlet under color. Right. So which are the other charge? So the other charge, this peculiar assignment, let me do it here not to make a mistake.
It includes the normalization.
Sorry?
It's the normalization T3Q.
Yeah, you can deduce it from the electric charge, to be precise. Such the electric charge is y, and where y is this quantum number, and this q, no, these are double, so this is u left, this is u left, u left. So this is the table. So this is our freedom. So nature is telling us these quantum numbers. Okay, once you decide what it is, of course you determine by measurements. So you see that these are colored, okay, and they belong to the fundamental of SU3. these two belong to fundamental of SU2, and so on. Again, this is something you cannot decide a priori, you decide by experiment, but that is the end of the story. And then, because of this quantum number, the covariant derivative tells you how they interact with the gauge field. 1 point to note here, and we'll come back later tomorrow. First of all, this U1 assignment is very peculiar, right? So this is very simple. So again, all these the quarks are triplet, or those that feel the weak interaction are doublet. These numbers are a bit random. Not only are bit random, but also for U1 symmetries, they could, in principle, could be pi. It doesn't need to be a rational number. Okay? So this is the problem of the quantization of U1 So why this is so clearly, it's, in my opinion, one of the clear indications that maybe these things has to be embedded into a bigger group where this is just the eigenvalue of a bigger monotone symmetry. But again, it's one of the reasons why we think the standard model needs to be complete. Question? And then there are also these other very important things that we have these three replica of fields that, from the point of view of the long range forces, are identical. Really identical for the long range forces, but they have different level structure. Finally, one could see why, clearly, if you want to make the things more symmetric and at this level, the neutrinos have no mass. Why we don't put here new right? We can put new right. New right would be a field that is right-handed, so you expect it to be and non-color, so you expect it to be singlet here. And then, depending on these rule here you have to put that 0 hypercharge, okay, because it has 0 electric charge, right-handed. So this field clearly do not belong to the table because it would be something that doesn't feel any of the three long-range forces. So if you want, I think it's consistent. I think most of people agree to define the standard model as the theory of the three long-range forces for the current fermion that feel these curves. So the neutrino is something, if this would be something different, and that doesn't feel this force, doesn't belong to the. Okay, here there's no coupling. Here, now let's give a look to the Higgs potential. Here there is a kinetic part. We can write it for complete. There is a kinetic part, and then there is a potential part that depends only on quadratic phi, and this potential part we write it as lambda normalization. I can write it like this. Such the minimum is when quadratic phi is equal to p. And so there are basically two couplings, lambda and v. Or if you expand this, if you expand it, I get lambda over 4 quadratic phi square, and then I get 8 minus. So there is what some people call master, or if you want, there is a term associated to a quadratic operator. So this is the only relevant coupling of the Lagrange. This is very important. We went through the discussion. So this is the only term that has an energy dependence in our as an energy scale with energy in our Lagrangian, and is what determines this V. So the mu is just lambda times V. And that determines the complete spectrum of the theory because, as you know, all the other masses are proportional to this. So clearly, this is a very important indication, okay, that the theory has a built-in scale, which is Higgs depth or Higgs mass, is the same thing because they are all controlled by the same combination of coupling. And this, I think, is a very interesting indication, and I think we have to take into account. Okay, here. Only two couplings, so the one I want to say is there are only two couplings. Finally, there is the Fukawa sector, which is the sector that we put in to describe all fermion masses, which is the sector that contains more free parameters in the theory. So we fellow sector. What is that? The fellow sector is very simple. Okay, I can write it like this. So these are the only interaction between two fermions, and the Higgs phi c is just a rewriting of the Higgs field such that it gives birth to the Acom component rather than the Dow component. I hope this is well known. If not, we'll discuss it later on. So again, it's just if you ask which are the interaction I can write between the fermions, okay, two fermions and the scalar are of this type. Here, in principle, I can put this flavor I. So these are 3 by 3 complex. And I have 3 of them. So you see, it's a huge number of parameters. And most of them are unphysical because it turned out that I can rotate the way these phases by field redefinition, but something physical remain and are, first of all, the masses of the fermions. Look at this term here, maybe I should have told you first. I choose the normalization where my Higgs field, the wave of the Higgs field, I write it like this. So this is the one I proposed before. And so when I look at this term, let's assume just one generation of fermions. So if I have 2 bar left YV derived by when the Higgs go to its bed, like this, you get here, this is a doublet, so it's 2 bar left, this is my coupling. Here, then I have my field, the Higgs field which is 0V, and then I have the square root of 2, and then I have my right, you see that this term give me YV square root of 2. So this is a master of our fermions, which, okay, so clearly these terms are needed to generate the masses of the fermions, and yeah, let me give you the answer, and then tomorrow we'll do the demonstration. So how many terms are there? In practice, the physical parameters are 4. There are 6 quark masses, 3 electron masses, 3 so-called sequence angles, and 1 phase. So after this is all these terms originate from this sector here. So it's clearly the largest number of free parameters from the largest number of free parameters. The very interesting things here is that, as we saw from the spectrum, you know very well, the spectrum of the standard model, it's highly non-trivial. Okay, so the top mass is 174. The lightest, the next heaviest is the big quark, which is 4 GeV, and all the others are very, very light. clearly this coupling, if the comes from UV theory, retains some information which is non-trivial, is much more insightful with respect to the gauge coupling, which are very natural. Okay. So clearly, if this interaction is the remnant of some high-energy theory, this energy theory has to have a non-trivial structure from the point of view of this index ij, which is flavor, because the coupling chain basically follows the magnitude. So look at how you get the masses. So clearly the masses of all the fermions in the standard model are the type some coupling of the fermion, the back divided square root of 2. So if I look at the mass of the top is 174, and then my coupling is basically 1, while the mass of the electron is 0.5 MeV, so this is the top of the electron, then my coupling is 10. So clearly, this coupling is an interesting hint again of something that the completion is non-trivial. Not only that, but it's also a hint that if you want to complete the theory with all the higher dimension operators, which I have raised, you have to be careful because you can spoil this structure, which is indeed is the leading structure in terms of operator dimension 4, but has some very small coupling. So you can easily destabilize it with the operator, even if they are irrelevant, if they have bigger coupling. So this is a very important. Okay, so basically with this I exhausted all what I want to tell you in terms of general terms about the standard model. So I hope probably this you've seen it already in your course, but it was useful to have a one. So indeed, what the plan, the following plan is to basically look in more detail about the symmetries hidden here in this Lagrangian, in particular the global symmetries related to the fact of this flavor structure here, which, and also the possible instability here of this mass term, which are kind of indication where we have to look for if you want to do a completion of the study. So in terms of timing, probably it's not optimal, but I think it's good to start with the first of this indication, which is the so-called hierarchy problem. That is to look at why we think the fact that we have this scale here is an indication that the first nearby scale, so the first, I told you, this would have been any scale, but there has to be something not far from this value here, which is connected to V, which is 140 GeV, if you want to make this theory a consistent. Okay, so let me erase this. Maybe we start and then we continue tomorrow. Okay, so yes.
Let me know when, or how many minutes you need to start to introduce.
So, tell me, how much time do I have?
Practically, the time is
Already.
We can start with if you want, we can start with the questions.
That maybe make more sense because because otherwise we will be opening a new chapter, and I will not be able to do it in 5 minutes. So I think it makes sense because that this way basically I had introduced all the ingredients. So basically I hope you get this nice view of again what I hope that what is the standard model and why we want to go beyond. And because maybe we can close here and have discussion, and then tomorrow we start with the bit more technical aspect like hierarchy problem and flavor symmetries. Okay.
Let's thanks the speaker. Please, if there are questions.
Maybe it was a bit too simple today. I don't know, to give me
also simple question. I suggest students to no, that's for curiosity.
part of the lecture, you call the mass system relevant interaction. Why interaction? So I understand.
No, it's a good question. So, well, because it's you can view it as an interaction between two fields. So, if you want, it is. You can think of your Lagrangian. I define the field from the kinetic part, which is the one that contains only derivative. So, for instance, let's look at the scalar field, right? This I can think of it. I can even treat it as a perturbation with respect to this term. Of course, the fact that it's quadratic implies that I can use it, can treat it as the Gaussian term and can solve exactly the thing. But still, I can treat it as an interaction. So I can treat this as an interaction because this is an interaction between two fields at the same point controlled by m squared. Okay, so I think there is no reason to distinguish from lambda. It's conceptually very similar to this term. Okay? Of course, usually we treat all these to define the free field case. Right? But for the sake of since I define the canonical dimension by this term, all the rest, because you see, this term is the one that contains no free parameter. The mass, if you want, is an extra parameter. This is why I can treat it as an interaction. I call it an interaction. Then, how I want to treat it in perturbation theory is a different story. But it's an extra parameter that I put in my Lagrange, while here I have no free choice. So this is the one I need to use to define the canonical dimension of the field, while all the rest one will define the canonical dimension of interaction. Right.
Probably you will discuss this later on, but the scale that you are using, often a physical scale,
yes.
Something happens. Will you discuss or will you comment now when this scale is the gravitational scale? So if you will discuss it in the future, then I wait. Otherwise,
well, no, it's a very good point, and I think I will not discuss it later. So I think it's good to discuss it now. So I think, yeah, the point is, renormalization. The nice things of renormalization is that we can always express things in terms of physical scale. Okay, and as I was saying before, for instance, what is the process of renormalization? This is a very important point. Is the part that, for instance, suppose that you know the theory at the gravitational theory at the gravitational scale, things will change dramatically. Okay, we don't even know if quantum field theory will probably be a different type of setup. This is why I express very much. I think below a certain scale, we think, at least for sure, we know in a bottom-up approach that up to a certain energy, the one we explore, quantum field theory is a good framework. Okay? In this good framework, quantum field theory is not obvious that it's extrapolable up to arbitrary high energy. For sure, when we end up to energy when gravitational interaction become relevant, my description of the action, which is not anymore there, again, it doesn't make sense because I have to put the variation of the matrix, so clearly it becomes more complicated. Okay? On the other hand, the beauty of quantum field theory is the fact that if I know the theory at a certain energy, U1, and then I know the theory and I want to see how the theory change, this is still in a regime where QFT holds, okay? And here I have my coupling at one energy, and here is my coupling. This change is completely determined by the theory. Okay? And again, when I have a quantum field theory that works, I can go from one energy to the other, and again, if the theory is normalizable, it means that I fix the coupling one scale and all the rest is fixed. If the coupling is not normalizable, I have to add other terms, but again, everything is completely fixed. The beauty and the disadvantage of renormalizable quantum field theory is that indeed, no matter what will be the gravitational effect, so will just reabsorb it in the value of this coupling. And then you can only observe this change here. And you are insensitive scale in which are involved. The real quantitative theories has different energy scale, which so far we've seen work very well. It worked well from QED to the one Versailles theory, and hopefully also above, because the indication we have of the gravitational theory, the gravitational scale is much higher.
Giancarlo?
If you want a complementary thing, answer to what Fedele said is that after all, we cannot talk on normalizable theory all the way, because we don't know. There is gravity anyway, so we cannot talk of.
But there are basically, okay, now we're discussing, there are basically two options. Either, for instance, we end up embedding everything in an asymptotically free theory, like QCD. For instance, QCD is an asymptotically free theory that is really in the UV becomes free. So it's automatically insensitive. Really, it's a free theory. So then there is gravity, which will not affect the QCD, okay, because it's completely free. But we don't know if the embedding will be an asymptotically free theory. Okay? So it could be that if you embed, maybe it's one of the possibilities that you embed everything in an asymptotically free theory that becomes completely free in the ultraviolet, okay? And then it's somehow completely decoupled from gravity. The other option is that really you modify your TFT. For instance, again, we don't even, maybe space-time is quantized. Okay? Space-time, there is a fundamental law. So clearly there are indications of a fundamental scale, which is the Planck scale, but however it's way beyond any of the accessible scale. And the point that we don't have indication of what is, so we have indication of this scale, but we cannot find traces of this scale in our camera. You see, so, and again, I want to stress this point once more for the young people. So renormalization in context of quantum field theory, okay, four-dimensional quantum field theory. When we think of a bare coupling, what is the bare coupling? The bare coupling is the coupling you put in your Lagrangian. That in coupling you have to define at some scale. Okay? So when you basically do the UV renormalization, you extrapolate and you introduce a cutoff, you extrapolate the validity of your theory up to arbitrary high energy. And this is why you see that your bare coupling diverge. Okay? And this is nothing but the fact that you have defined your theory at the wrong scale and then with respect to the scale to which you do your experiment. If you don't pretend to do your integral up to arbitrary scale, but only within physical regime, there are no divergences. Okay? There are only finite running of the coupling between one value and the other value. Suppose the fundamental theory is a lattice. It's possible. Okay? Then there are no divergences because up to a certain point, then your integral are finite. But suppose that the lattice spacing is the Planck scale, which could well be, then clearly your bare coupling would be the coupling at the Planck scale. But what you measure is the coupling at the proton mass or the B mass, and then you start from the coupling at the Planck scale, you do the calculation, you integrate, and then you cancel all this effect from the Planck scale up to the proton. And this is the normalization. Okay? And then the only thing that matters is from the proton to the B, for instance, this is what you're able to measure. I hope this
may I ask a naive question? As was there is the table here that when you wrote that table writing down the assignment of hypercharge, you said, okay, we are choosing those values to basically get the right electric charge. Okay.
Yeah.
At some point, and this is what we also teach in our courses. And but then at some point you said, well, could have been different. Say something like that. There is something
yeah, there are
that let you tell
so,
that.
The point, okay, what I meant is that was a bit brief because what I meant is if I only have a U1 theory, suppose I have only U1 theory, can be anything. There is the U1 theory doesn't tell you. The U1 theory is a theory where your fermions are invariant under sheet. This Q can be anything. Doesn't need to be quantized. Okay. The point that here also, I mean, there is the coupling, but then there is the charge. For the non-aphelion cases, for instance, here, it's true also there is the overall freedom in defining the coupling. So But then once you define it and you say this is a triplet, then I mean how this relative change is completely fixed by the quantum numbers. Okay? It's something that you don't have here. Quantum number can be changed. So in principle, if I only look at U1 theory, it could be anything. However, okay, there are two things. First of all, there are anomalies. Okay, and okay, this is probably maybe some of you know. So the quantum anomalies, that is, if you play randomly with these things, you generate some problems in your integral, and then you break the symmetries of the Lagrangian by the quantum effect, and you see that only specific assignment of upper charge would cancel this. Can we take this as an indication that they have to be like this? Some people say yes, this could be an indication. However, and it's true that if I stop the assignment here, let's see, there are no other assignments that would cancel the number. Okay? No way. However, as soon as I enlarge the spectrum of the here, for instance, I put already this guy here, then you see there are other options with milli charge, everything is somehow possible. There are other things that would still cancel the anomalies and would be possible. So that, okay, then you see, that's it. This is the theory of everything, and then there is gravity. It would be a bit unsafe, and then okay, then you see, then this is completely fixed by the cancellation of anomalies. This is an option. Another option, which I like more, is to say, well, since this appear with these non-obvious numbers, they maybe are the eigenvalue of a non-abelian group where these appear as specific, exactly like T3 or so on. For instance, we can embed these two guys into right, and this will be doesn't work like this because they are not identical, but then we can embed these into very nice embedding with I is that then there is an SU2 right and the B minus L. And then you see that if I just have a B minus L which differentiates quark and leptons, and this B minus L will be here. The B minus L will be 1/3, 1/3, 1/3, and then you see here I have my other charge will be T3 right plus B minus L half. Then okay, still I have U1, but then I can unify the U1 with SU3 color, sorry, with SU3 color to SU4, which is Pati-Salam, and then everything is non-abelian, no free charge. Okay? Charge of the quark and the leptons are completely together, so I understand the quantization of the electric charge. So why proton and electron have the same opposite charge? Because they belong to the same field. This, in my opinion, is a much nicer explanation and much more resistant than to the extension in terms of fields.
They always introduce a particle, like Seiberg. You introduce a particle, doesn't cancel anomaly. I invented a particle.
So in my opinion, the argument of cancellation is weak.
Like also the gym happened like that.
It's weak. Why? On the other hand, the fact that this is really it's in non-trivial relation with this, I think it clearly points to an embedding of all the Fermi into simple representation of bigger non-abelian groups. The point is where, okay? That we don't know, but the indication that this should happen. This is why the standard model effective theory really makes sense. So I think we need to extend the theory, and then what we have to understand is where is the cutoff, and this we cannot determine by these numbers. So this one I'm going to tell you there has to be something else. And then is on the other hand the property of the Lagrangian, this peculiar variability that contains some indication of where it is.
Probably a question. The only non-gauge interaction inside.
Exactly.
So since we believe that for some reason we believe in some sense that gauge interaction were the preferred ones, were to be the fundamental ones, one expects that this could be a remnant of some kind of gauge theory. But one of the strongest arguments in favor of the gauge theory was that they were renormalized. Now, if I lose this constraint, I don't care about renormalizability because I don't want this theory anyway to be somehow good up to infinite energy. What gives the gauge theory their special Meaning, apart from the fact that what we see are gauge theories, but the one we don't see, why should we think about gauge theories at this level?
So I mean, you touch a very important point, but so let me say something. So you see, the message is, again, think about QED, okay, and then in QED, you just have this coupling, the electron, so the alpha, sorry, which doesn't tell you anything about the Fermi theory. Really just, and it's basically, then this goes basically somehow to determine the coupling here of these parts. Gauge theories are kind of, they are nice, they describe the long range forces, but they are really insensitive to the UV. On the other hand, all the other interactions are the interesting ones. So that's exactly the point. I raised my standard model Lagrange. So in my standard model Lagrange, my philosophy is the gauge coupling, they are what they are. They will unify. We don't know. Really, it's a kind of dressing of the theory with these long range forces. So what we want to understand what's next, okay, we have to look to the non-gauge coupling, which are the Yukawa and the Higgs sector. These are the only known long-range forces, okay, which contains clearly, so not only the Yukawa but also the Higgs. These are the two things where we have interaction which are not long-range forces, which are, so these long-range forces are kind of insensitive to the UV. While the Higgs potential and the Yukawa are clearly more likely remnant of something else. What is this something else? Is a gauge, is a non-gauge? That's we don't know. Okay. For instance, we have seen in the case of the Fermi theory that this was indeed a remnant of a gauge theory, but dressed with a non-trivial symmetry breaking sector. So clearly, my favorite, but this is my favorite option. But this is motivated by the fact that here I would like to extend the gauge structure. I think a very natural setup, which is the old classical model building, is to a large gauge group, break spontaneously, and there are a lot of options which are still unexplored, okay? In a way that you will be able to explain why these assume this value here, and also explain why the Higgs mass is what it is. So this, I think, is the nice philosophy. Really try to extend your field content, okay, with different scale, that, and possibly also the gauge sector. The gauge sector is I mean, we know the philosophy of extending the gauge is that because these are well behaved, okay. You are right. You say I convince you that they don't. However, the non-normalizable theory also have an intrinsic validity regime. Okay, so I think there are plus and minus. So I don't think the effective theory at the very end, so the one where we embed gravity will be an effective theory. There will be the theory of everything. Okay. Complicated thing, but basically doesn't mean it needs to be
and you still hope is the gauge theory. Then the final one.
This I don't know. I mean,
you don't have this faith.
Gauge theory can even emerge at energies as is a symmetry, okay, that emerge it's just related to these invariants. Doesn't, I mean, the UV doesn't, there is also the idea of possible emergent gauge theory. This needs to be the principle valid. The settle need to be modified if you want to embed it with gravity.
Just
comment?
Another answer that you would have given to him in a different context is to put in front of his face the table, for instance, Barbieri Strumia for the STU of the standard model of the parameter of the standard model, the deviation of the standard model, how much they deviate. You write it as a higher dimensional operators, and then you say, these are much you deviate from gauge theories. And in the case of the electroweak sector, your typical table of the CKM that you wrote even for the in the paper you wrote with Nir and Perez.
Okay, but on the other way, we will go tomorrow on the various operators. But I think but the message is that really, yeah, there are two different things in the standard model which are a bit mixed up, which is the gauge and the non-gauge. And I completely give it the fact that I think is the non-gauge the only one that can hope to give us some information, because the gauge is insensitive. Okay, the gauge runs logarithmically, doesn't care about the UV. So this is the thing. If the UV contains other gauge, I think the strongest deviation is this.
Okay, so that's the answer.
Stefano,
More or less is on the same way. So the take-home message is that we can survive with effective field theory, for all our life, or at
No,
some
no,
point
no,
you
no.
really would like to have supranormalizable theories?
I think effective theory are nice just because they tell you how
Is a
to
tool.
proceed. It's a tool. It's a tool.
Okay.
Effective theory is a tool.
Okay, is a tool.
It's a tool. Actually, this is not again a very important point because now there are people who think, for instance, this math, they use it as a theory, as a not a theory battery. This is the most stupid statement I heard. So I mean, effective theories are effective, okay? And this
Is a nice tool.
So are a nice tool. A nice tool to go from one scale to the next scale. It's a beautiful tool, but you have to be careful that it's a tool. And if you use effective theories without guidance on the UV, you make mistakes. Okay? So you really have to be careful using effective theories. So
you
today,
miss Taiwan CISO, you miss W mass.
On the other hand, I mean, are useful, so we should not be afraid of using effective theory. So, yeah, sorry, but today indeed I give the positive message on effective theory, which is it. I work on my life on effective theories, and I think are useful, but I think we have to find the new completion, the next step, right? Absolutely, and this has to be a consistent UV completion. I really there too many parameters however, they also are predictive, so if one use them well, are useful.
A comment from Salvatore.
Yeah.
I like a lot this presentation. I want to just put a point to discuss. Imagine that I don't care about gauge, and I put in this table random, and then in some sense GL4 group, without caring about gauge. What is the counter indication? Because in that case, I have two spin particles and.
That you can do, but the point is, okay, maybe also this is which is the contradiction of the standard model and gravity. That's
exactly. But in your perspective, having
so my perspective, indeed, I give you two arguments which are this one is here. So I really don't like this 5-order magnitude here, which could be put by hand. Okay, and also this assignment here, which I told you. However, you are right that if I don't put anything else, in a sense, this is less of a problem because then you would justify by binomial cancellation. The only this will go back tomorrow. So there are three things. So these are really unexplained 5-order magnitude numbers, but okay, you can be happy with that. At the end, it's a still small set of numbers. A bit of random structure of this, but again, you can justify this by anomalies. The third thing where I'm unhappy is about the Higgs mass, which I compute. So there is only one scale here, which is the Higgs value, 246 GeV. And the Planck scale is 10 to the 18 GeV. What keeps these two scales separated? This is the thing. It's true, we are not able, honestly, to compute the quantum correction to the Higgs mass. So if I tell you, if I were able, I would write a paper. So I think we are not able. Right? Those who claim they are able, they are just doing naive calculation. We are not able. It could be that this somehow miraculously these things will cancel, but it's unlikely. Okay, so clearly we have indication of two very different scales, the Planck scale and the Higgs scale. What keeps them separated? That is why, in my opinion, this tower is the more natural explanation. And this tower can then have all the degrees of freedom to explain also these other things. So this is my philosophy. But I agree that there are people who think, okay, that's it. There is standard model. But for instance, again, other things are neutrino masses. Neutrino masses also are even more puzzling, no? Completely different. Neutrino masses you explain so nicely with the seesaw mechanism. That means that there is another scale. Where this scale will destabilize the Higgs. And therefore, you're back to the Higgs of making something consistent. So we have indications there is something else. I don't want to even invoke dark matter, but neutrinos are there, okay? And they have a coupling which in these units would be 10 to the minus 12. So I don't like 10 to the minus 12 compared to the ones. So I try to explain as a ratio of scale. With C2 I can do that, but then if C2 it means I have a heavy scale. And this heavy scale will destabilize the Higgs. And therefore, I need to protect the Higgs, and then I have to start to make this construction.
In all this framework, what about supersymmetry?
So I think supersymmetry can be there. We don't know. It's an extension. It's a beautiful idea. Okay? And I think so. I work a lot on supersymmetry, so supersymmetric extension. So I now start to be more agnostic in the sense that, to be honest, we don't have any. So supersymmetry is nice because, for instance, first of all, it's nice because it is the biggest symmetry, extra symmetry I can put in addition to these gauge symmetries and space-time. Okay, the only extra thing makes it consistent in quantum field theory is graded algebra and supersymmetry. But there is no indication that this supersymmetry has to be broken. Actually, for sure it's broken, because otherwise we won't be here discussing, okay? So it's broken. At which scale is broken? That this is the big question mark. For several years, we were thinking, okay, this breaking is nearby the electron scale, and this has stabilized the Higgs. That was the argument for a low-scale supersymmetry, or the MSSM, and so on. Now we have not seen it nearby, clearly. Could be just a little bit higher, it's possible, but at this point, if you miss the connection to the Higgs, can be arbitrarily high. So it could be, yeah, it could be a supergravity theory, but at much higher end. So, as I said, I'm a bit agnostic. So I think I like it, could well be, but I cannot make a claim that has to be nearby.
Also, concerning what you said, there is also a negative thing concerning, because one of the beautiful things of supersymmetry was there around the electroweak scale that you would have expected in a positive case also the dark matter to be seen at CERN, but none of the two possibilities has failed. And also, I think this has changed completely the concept compared to a few years ago. Also, Xenon hasn't seen dark matter to very little masses. So
Yeah. So, but this could be an argument. Indeed, it's an argument against the MSSM in the simplest implementation.
Exactly.
The good things were three: gauge coupled unification, which also is a bit stretched. Still, is the one which is less stretched because it's only logarithmic. So, dark matter candidate and stabilization of the Higgs. Now, stabilization of the Higgs and dark matter candidate are lost, in the sense that the Higgs, you still now have a tuning of 10 to minus 4 with supersymmetry, so it's bad, and the Fuzzy candidate in the minimal version. Okay, then you can think of more extended version, but then, okay.
But the beauty has already stayed.
Other question? If there are no other questions, let's thank again. We will see tomorrow.